Okay, that last little soiree was a little bit longer than I wanted it to be, but here we are. Now, look what happens here. If this is a conducting rod, like say this is some kind of high conducting silver, and this is a nice, very nice. Oh, let's say it's silver too. All right, so those are both high conductors. So it falls through here, bam! It's just the weight of it, and the magnetic field, and let's say there's no kinetic friction between the rod because the only force in the rod weight that it falls. Suppose, okay, so here it is. It's falling between these two copper tracks. Okay, it's falling between here. Okay, now as it's falling, as it's falling, it induces. Now here's kind of the cool part. It induces a magnetic field. All right, I think they're saying it falls through a magnetic field going this way. It will also induce a magnetic field, but we're going to get to that later. And that'll create a back EMF. All right, so there's a magnetic field coming out this way. There's a strong magnetic, so we drop this thing inside this magnetic field. All right, so the magnetic field is increasing in here. The area is the magnetic field is staying constant, but there's getting more of it. But the area of it is definitely increasing. Okay, as it's falling, and eventually, notice it's going to create a force going up. So it's going to slow down as it falls. Okay, and I've got a cool demo of that I might bring in on Wednesday too. Okay, in other words, this thing's falling, right? It's falling, and but there's a force now that's going up this way because the current's going this way, and it feels that force. It feels a force now that's going up. Put your fingers out this way. Okay. Pop your thumb out that way, and now the top of your hand comes the force. So slow it down. Because if it went this way, it would increase it, and that's why it opposes the law of conservation of energy. So here's what we're after. The magnetic flux is equal to B times A. I disagree with that. You also got to put the cosine there, Wiley. That's where we started this whole thing. So, of course, I jump right into 22.3. I miss all their explanations to start with. And here we go. The change in flux or the change in time. This is not an E field. This is the EMF. All right? That's the electromagnetic, that's the electric flux through there. Okay? I spent the whole first thing explaining the normal. Here it is again. Okay? All right? So this, when it's parallel to when it's parallel to the normal, notice how the coil here is perpendicular to the magnetic field. So perpendicular, that'd be the cosine of 90, which is 0. What we're looking at is the normal. Here it is. Here's our normal right here. So it's the cosine of 0 because it's what's the angle it makes with the magnetic field? 0. So that's a maximum. So the magnetic flux is proportional to the number of field lines that pass through the surface of those magnetic field lines. So changing magnetic field, and we can change it by either rotating the object, by changing the area, or by changing the magnetic field. It's BA cosine of the angle. Here's magnetic. Here's the real equation. BA times the and you can change any one of those three. Boy, is that a conceptual question or what? All right, so there we go. Faraday's law of inductance. Here it is. And this is where we started the whole thing, is equal to the change in flux or the change in time. Dun, 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 dun. We are more than halfway through this chapter already, and it all combines the same big idea. Okay? So a coil consists of 20 turns. Each turn has an area of 0.05 meters squared. A magnetic field is perpendicular to the surface. That means it's perpendicular to the surface, so what does that look like? That looks like this. Okay? Initially, the magnitude of the electric field is 0.05 teslas, and 0.1 seconds later, it's increased. So somebody increases the magnetic field going through there. All right. So now all we have to worry about, since the cosine of 0 is 1, we just have to worry about the coil's not changing, the end doesn't change. This negative sign is for the polarity. Okay? So it's negative B initial minus B final, B initial, or B final minus B initial, I'm sorry, divided by 0.1 seconds. It comes out to be negative 3 times 10 to the negative 3 volts. Not much voltage. If you get enough coil in there, notice if you increase in, if you can get enough coil in there, you can get quite a bit of voltage. However, what happens? The more coil that you have, the heavier it is, so the more energy it takes to turn it. The more coal you have to scoop out of the ground and burn to get it to move. Okay? 2 pots are placed on an induction stove at the same time. The stove itself is cool to touch. The water in the ferromagnetic pot is boiling because it's creating a resistance. Conducting surface, ferromagnetic material. Okay? It's got a magnetic field. All right? This is made out, so they're probably keeping a constant magnetic field. And they probably have a little electric thing churning around in here. So it's changing the flux all the time, heating up a coil. But it's just that coil, so the stove is cool. I bet you that. And then Lenz's law I will do for you on Wednesday. All right? Cool beans.